for now. I'll just say hi, everyone. Welcome to the November TEPS seminar. I know you're all used to seeing Professor Eve Lee usually facilitating these, but she's away at a conference, so I'll be facilitating in her absence. Before I pass the mic over, I just wanted to remind everyone that the presentation itself usually goes for about 40 to 45 minutes, and we'll have a short Q&A, about 10-15 minute Q&A afterwards. So during the Q&A, if you have any questions, just raise your hand using the participant tab below, and I'll just keep track of that when we get to that. If there are no further questions or anything else, I'll pass it over to Professor Catherine Naish to give the introductory remarks for Dr. Jason Barnes.
All right, thanks very much. Good afternoon / morning to Jason, I think, to everyone here. So I'm very pleased to introduce Dr. Jason Barnes. I met Jason in 2004 in Tucson, Arizona, where he was just completing his PhD and I was starting my PhD. He stayed on to do a 2-year postdoc working with the Visual and Infrared Mapping Spectrometer on Cassini, and then moved on to NASA Ames in 2007, where he worked on the Kepler mission. So throughout his career, Dr. Barnes has had a joint interest in both spectral characteristics of icy worlds and also exoplanets. So that complements the group here rather well, I think. In 2008, he got a position at the University of Idaho, where he remains to this day as, I think you're still an associate professor, or have you ranked up yet?
No, they promoted me a couple of years ago. So
okay, congratulations. So professor of physics at the University of Idaho. And he's also the deputy PI of the recently selected Dragonfly mission, which is what he is going to speak about today. So Jason, take it away whenever you're ready.
Okay, thanks. Good to see so many people I know, including John. John Moores and I were also together at Arizona for a while with Catherine, and I know Nick from other places, so hey, everybody. Today's talk isn't exactly about exoplanetary technology so much as, extraterrestrial technology, but it's pretty close. Well, I'll see if I can make the connection. So yeah. 4 or 5 years ago, we got the idea in our heads to propose to NASA a nuclear interplanetary quadcopter, which sounds pretty crazy when you put it that way. But I hope to convince you by the end here that far from being crazy, this is really kind of one of the neatest and smartest things that NASA could be doing with its money. So for those of you that are true exoplanetary people that haven't thought about the solar system for a while, let's think back. When you kind of look at the solar system in the big picture, there's really only 4 planets that have both a solid surface and a thick atmosphere, right? There's plenty of places like Jupiter and Saturn and HD 289458b that have all gas. It's all gas all the way down, and there's no solid surface to speak of at all. And there's plenty of places like the Moon and Mercury and Ceres that have a solid surface but don't have any atmosphere at all. But if you're talking about planets with a solid surface and an atmosphere that interacts with it, like we have here on Earth, there's really just Venus, Earth, Mars, and Titan. And of these 4, Titan is in many ways most similar to the Earth. Okay, not always. First of all, it's like freaking freezing out there, okay? It's 94 Kelvin because you're out 10 times further from the sun than the Earth. And because of that, the surface and the outer crust of Titan is not made of rock like it is for Venus, Earth, and Mars, but it's rather made of water ice. So water ice is a building block on Titan and forms a large fraction of its volume and mass, and most of its entire crust. And that surface is, it's not like a glacier ice where you're like near the melting point and things flow or anything. At 94 Kelvin, the ice there is like rock on Earth. It's a completely solid surface. So because of that, there's no water in the atmosphere. And instead, there are another element plays the role of water, methane. So you are like with water on Earth, where water is sort of near its triple point. It can form solid, liquid, and gas. For Titan, methane is near its triple point. And in fact, we do see clouds of liquid methane on Titan, lakes and seas, as we'll see in a bit, of liquid methane. Yeah,
Are you sharing slides? Because I can't see them.
I thought I was sharing slides, but I am not. You're right.
I thought this was all still part of the intro. I thought Jason was just getting really excited before even going into the slides.
Sorry. Yeah, no, we tested sharing slides earlier, so I thought I kind of assumed we were there. So I appreciate you said you guys should speak up earlier. Geez, how long were you gonna let me go?
I like the hand waving.
Oh, I do lots of that, so you'll get used to it. All right, so this is the intricate chart that I was pointing to that no one could see. Okay, so looking at the composition of the atmospheres, though, they're actually of these 4 planets. I'm promoting Titan. You know, it's as cool as the planet, so it's allowed to be up there. The atmospheric densities are quite different, of course. Venus is 100 times thicker than Earth's. Mars's is 100 times thinner than Earth's, but Titan's is just right. It's sort of about the same pressure and density as Earth's atmosphere. In terms of composition as well, Venus's and Mars's atmospheres are both totally CO2. But Earth's and Titan's atmospheres are both dominated by nitrogen. So it's actually quite similar to the Earth, and actually makes it easier to test, flying things, which also helps. But the idea behind flying a quadcopter is that the atmospheric pressure is 1.5 times the Earth's atmospheric pressure, but the density is 4 times the density on Earth just because of the temperature, right? That's a PV equals nRT thing. So the density of the atmosphere is 4 times as high as on Earth. And the gravity is about 1/7 the gravity on Earth. It's only about a little less than 2 meters per second squared, not grams per cubic centimeter. So this is a different thing. But the gravity is about 1/7, about 1.3 meters per second squared. So it's actually the easiest place to fly in the solar system on Titan. So if you're going to fly anywhere, if it's going to work anywhere, it would work on Titan. Much easier than on Mars, of course, where the atmosphere is hella thin, or Venus, where the temperature is hot enough to melt your entire spacecraft. Another way to think of Titan, sort of in context with its solar system brethren, is in terms of where we might look for liquid water. So astrobiologists, well, astronomers who claim to be astrobiologists kind of take a step back. We try to think of what are the elements you need for life. There's probably a lot more than this, but like at a bare minimum, you're going to definitely need energy, some sort of solvent, presumably water, and carbon to be able to build up complex molecules. So looking in our solar system, where do we have that? The energy is actually the easiest part of the equation. Even at Titan, the sunlight is plenty to be able to drive biological reactions on the surface if that's what you need. And even if you don't have that, there's other sources of energy underneath the surface, like radiogenic heating or potential chemical sources under the surface, like you have at the bottom of Earth's ocean. So energy is probably pretty easy to obtain any place you look. Water is also surprisingly common in our solar system, okay? When we did our initial reconnaissance of the solar system, we kind of sent Voyager out looking at the outer solar system, and it saw a bunch of icy moons, and they were like, okay, those are pretty cool, ice chunks. But it wasn't until the Galileo mission around 25 years ago that we recognized that many of those icy moons aren't just ice all the way down, but rather have ice on their very surfaces. And then as you drill down lower and the pressure increases, that ice converts to liquid water. And many of these planets have a liquid water mantle below that. In particular, Europa was the first one to be identified with that. And surprisingly, there's more water on Europa than on Earth. Okay, so we think of Earth as the ocean planet, okay, but that's only if you're a surface chauvinist. If you actually are willing to consider water beneath the surface, Europa has quite a bit more water than even we have here. Looking even more broadly, I mean, Jupiter's moon Ganymede, which has a much thicker ice crust, also has a thicker water ocean and has maybe 6 times the amount of water as on Earth. And Titan has even more than that. We think that Titan probably has more than 10 times the liquid water that we have on Earth. Yes, we think that maybe Mars had some water in its past, but like not very much in comparison. And really, Saturn's other moon, Enceladus, should be on this chart. Enceladus, of course, is a tiny little moon, only 500 kilometers across, but also has some liquid water. But its total volume of water is smaller as well. So really, if you're looking for places with water in the solar system, icy moons, which we now call ocean worlds for this reason, are really a great place to look. But when you're looking at the ocean worlds, what you're missing is this last element here, carbon. And that's where Titan really shines. So here's a video and a picture of what Titan looks like. On the left is what Titan looks like to your naked eye. Doesn't look like much, does it? That's because Titan, with that thick atmosphere, some fraction of that atmosphere is methane. And when the solar ultraviolet hits the methane in the upper atmosphere, it photolyzes it, breaks it into smaller bits that recombine into solid, about 1 micron organic particles that are known as Titan's haze. So this haze fills the atmosphere and prevents you from being able to see down to the surface. You probably don't have to worry about it there in Toronto, but earlier this year, we had a very similar experience here in Idaho when all those fires were going on the West Coast, and we couldn't see through our atmosphere either. So if you try to look through Titan's atmosphere in the visible, all you see is haze, and you're not able to see down to the surface. The video on the right, by contrast, is of Titan in the near infrared. So if you are looking, am I glitching out here? Did I glitch out there? All right, let's hopefully this.
No, I mean, you looked fine from our end.
Okay, so it's just PowerPoint that's crashing. Great. Okay. All right. Over on the right here, this is the view from the visual and infrared mapping spectrometer on Cassini that looks at longer wavelengths and is able to see through the haze. So if you were to sort of have eyes at 5 microns, about 10 times longer wavelength than our eyes can see, you'd see something like on the right here, where you see a variety of different surfaces. I mean, ignore the seams here. But all this brown stuff near the equator, we now understand to be sand dunes. So Titan's surface is covered by a lot of sand dunes. Here's a crater, an impact crater called Sinlap crater. We have these dry lake beds down here, Tui and Hote Regio. An area of mountains and channels here called Xanadu. And over here is where the Huygens probe landed. And our probe is going to land right down here, south. So there's actually quite a varied surface on the surface of Titan. And it turns out these sand dunes are not made of what sand is on Earth. They're actually made of organics. So we think that Titan's surface, because of all this haze, as this haze material is coming down, it eventually accumulates at the surface as solid organic particles in some way. We still don't know exactly what that process is, but a lot of Titan's surface seems to be covered in organic material. It was just really exciting to us from an astrobiological perspective, okay? Like, what happens when you get a bunch of carbon on the surface and you mix it with liquid water and you leave it for a while? We don't know, but presumably these are the conditions that formed life on Earth 4.5 billion years ago, something akin to this. So we would really like to know the outcome of that experiment, okay? When you mix liquid water and organics on a planetary surface, how far does that material progress toward biological activity, or are you able to form simple self-replicating molecules just in the time that you're able to leave those liquids and organics in contact? And we don't know the answer to that, but we'd like to find out. A potential snag is that the liquid water ocean on Titan is 100 kilometers down below the surface, and the organics are on the surface. Okay, so how are you going to get those two to mix? One way might be with what we would call like cryovolcano. This is basically like when you take Earth's rock and you melt it and ooze it onto the surface, that's a volcano. When you take Titan's rock and ooze it onto the surface. That's a volcano too, but Titan's rock is made of ice. So this is basically liquid water that would erupt onto the surface. And when it's on the surface, it'd be able to mix with the surface organics and potentially allow prebiotic chemistry to progress. This would be exciting if it happens, and we think it does, but it's kind of hard to say. It's kind of hard to identify what a volcano would look like if it was made of water. I mean, would it have the same structures as we see on volcanoes on Earth? Maybe, maybe not. On the left here is our best candidate for what a cryovolcano might be on Titan. This one is called Sotrafacula, Sotrapatera, maybe. Here is this big pit that may correspond to a volcanic caldera like those you see at the tops of volcanic mountains on Earth. Over here is a peak that we have named Doom Mons. The International Astronomical Union, in their infinite wisdom, have decided to name mountains on Titan after mountains in Middle Earth. So this is like, imagine the Eye of Sauron over Doom Mons here. It's a little colder though. But other than that, this is our best idea of what a cryovolcano might be on Titan. Nevertheless, when we sat down to really think about it, we decided that we weren't so sure that this was a cryovolcano as to bet $1 billion mission on it. I don't know. What do you think, Catherine? How confident are you?
You should read my 2018 astrobiology paper where I outlined the reasons for going to an impact crater over a volcano.
Yeah, I mean, if I knew for sure that this were absolutely for sure a cryovolcano, I think we might be able to make the case for it. But given the uncertainties and the difficulty of trying to propose a mission to NASA, it was not our highest priority candidate. Instead, we decided to go another place where we think where liquid water and solid organics have mixed, and that's to an impact crater. So this impact crater is called Selk Crater. It's about 80 kilometers across, rim to rim. And this is the rim here. It's a little bit icy. We have a couple of these brown sand dunes in the bottom and a bunch of icy but covered in organic material on the outside. And so in an impact on Earth or on Titan or many places in between, you're having a large object. This was probably around an 8-kilometer, 10-kilometer asteroid or comet that was slamming into Titan at maybe 20 kilometers per second. So as someone who teaches introductory physics often, the v squared in mv squared, once you're up at 20 kilometers per second, starts to dominate. And not to mention m is quite large as well, if you have a 10-kilometer wide body. So the amount of kinetic energy deposited by an impactor when it hits the surface like this is tremendous. And a majority of that energy ultimately ends up as heat and goes toward melting the target rock, in this case, ice. So we've estimated that on Titan, for Selk Crater here, this would have melted an impact melt lens of about 100 meters depth that Catherine has shown should possibly remain liquid for perhaps up to 10,000 years while it slowly cools from the sides. So Catherine has also seen these same kind of impact melts other places, right? This happens on Venus. Catherine sees it all the time on the moon. So impact melt isn't unusual. It happens all the time. And particularly on Titan, this is exciting because it offers an opportunity to melt not just rock, but water, and to allow that water to mix with organic material for potentially a very long period of time. It's really hard to do experiments over very large volumes and for a long time on Earth. As probably many of you know, it's kind of hard to do any experiment that lasts longer than a graduate student. So more than 6 years of an experiment is basically infinite. It's impossible. So Titan here may have been doing this experiment for a very long period, and we'd like to be able to get into this crater, actually drill into those formerly liquid water rocks of the impact melt lens, and to be able to see what happens when you melt liquid water on the surface and have it interact with organics for potentially a long period of time. So that is the tactical goal of Dragonfly. It's to land on Titan, measure the composition of both the solid organic sediments in the dunes and formerly liquid water at the bottom of the crater. But Titan actually shows many other exciting features other than just its chemistry. Titan is the only other place in the solar system, for instance, where it rains. I mean, rains and has that rain hit a solid surface. Clearly on Venus, the surface is too hot for rain, even exotic composition rain, to ever hit the surface. Mars does get some precipitation, but it's all like the Virga in Arizona, where you look up, you see it raining up there, but you don't feel anything down on the surface. But on Titan, we've seen thunderstorms of liquid methane. So these are some near infrared pictures of the mountain, of the thunderstorms on Titan. This color scheme uses green sort of to show down to the surface. The pink is showing you the haze that I talked about that pervades the atmosphere. And then the clouds show up as white or blue-white in this particular color combination. You can see that at any given time, like not a whole lot of Titan is covered in cloud, maybe a couple percent, whereas like 70 or 80% of Titan of Earth is covered in cloud at any given time. More than that if you live in the Pacific Northwest. Less if you live in the desert, but on average, Earth is maybe 70% covered in cloud. Titan has a much lower fractional cloud cover, but when it does rain, it seems to create very large storms that billow up all the way to the tropopause, which is 40 kilometers high. And we've seen evidence that that rain, hits the surface and colors the surface for a while. And that creates a really interesting geological system, a system that really resembles Earth more than any other place in terms of what its surface landforms resemble. And the reason for that is that Earth is like the only place where it's rain and rainfall erosion, fluvial erosion, that dominates the surface landforms. We were fortunate enough with Cassini to also send in addition to Cassini, which orbited Saturn, we landed a space probe on the surface of Titan called Huygens. Huygens, when it was coming down, was able to take images of some surface areas, and this is sort of a 3D model looking at a particular area that Huygens saw in 4 different angles. And this one shows these really intricate dendritic structures that are channels that channel away liquid methane when it rains, right? This is what you see everywhere on Earth. Even the most dry deserts, the Atacama Desert in Chile, still has little gullies from whenever it maybe only rains once every 10,000 years, but that's still enough to dominate the surface erosion. And that seems to be true at Titan as well. We have these intricate channels showing where the liquid methane has flowed off, which is only happens today on Titan and Earth that we know of. This is probably happening on who knows how many untold exoplanets, but we're not going to be able to get the information to know whether this is happening for probably several decades, if not more than that. On Titan, however, we're fortunate enough to get not just that, but a picture all the way down to the surface. So the Huygens probe wasn't actually designed to land. It was designed to be an atmospheric probe. But remember, 4 times Earth's atmospheric density, 1/7 the gravity. This thing actually had a parachute to slow it down so it could take better measurements as it went down. And that was enough to allow it to survive landing on the surface. And this is the image right here that it took when it landed. You guys probably don't appreciate this the way that Catherine and I do, but this is freaking amazing. Okay, there's only a couple places in our solar system where we have a picture from the surface. Okay, it's Venus, Earth, Mars, like Eros maybe, or an asteroid. I don't know if you nose count, and Titan. Okay, so this is the only icy surface that we have icy moon that we have a picture of from the surface. And just to orient you, this is sort of the equivalent picture you might see on Earth's moon. This, because it wasn't designed to take to last all the way to the ground, this picture is taken from pretty low down, okay? It's only taken from maybe 25 centimeters off the surface. So these aren't huge boulders or anything. These brightly colored objects are maybe fist size, 10 centimeter size ice chunks. And you'll notice that they're actually pretty rounded in comparison to rocks we've seen on the moon, which I guess this one doesn't include any here. But rocks you see on the moon tend to have been blasted out by impacts. They're particularly angular. And of course, there's no erosion to speak of on the moon to be able to round them down. But that's not true on Titan, evidently. You look at these rocks, they look like they're quite rounded, as if they've been perhaps tumbled down one of these river channels or eroded chemically or some other way. We don't know for sure how it happened. But they're evidently not just rocks fresh out of the ground. They've been altered since they've been there. In between these rocks is this dark brown granular stuff, which may be or be related to the organic sand dunes that we think cover a lot of the surface. But this is really exciting. First of all, to me, if you're going to try to convince a review panel that you're going to land on a new planet, you have to first convince them that there's places that are safe to land. And this is a particular problem, say, when we're contemplating landing on Europa. That place could be covered in like crazy spires and stuff of ice, and we wouldn't know it. And how do you design something to land on that? This looks very benign to the engineers. They like this, okay? This does not scare them. So that's a feature. So we know that there's both places to land, and it gives us a sense for what we might do if we were to land there with you know, an actual vehicle that was designed to do experiments on the surface. In addition to these areas near Titan's equator, where we have runoff, where does that methane eventually go? Well, it took us many years with Cassini before we were able to see Titan's North Pole. And this is the North Pole of Titan. Actually, the North Pole is like right there. And you can see these dark splotches. These dark splotches are lakes and seas of liquid methane at Titan's North Pole. So all this runoff eventually ends up at the North and South Pole, mostly the North Pole. But this is Punga Mare, this is Ligeia Mare, and this one down here is Kraken Mare. Those are the three big seas of Titan. And so these are maybe 100 meters deep, and they're the only open liquids anywhere that we know of in the universe except for the Earth, open surface liquids. We've seen subsurface lakes beneath glaciers on Mars, but these lakes are sitting there out open to the air. We've seen waves actually on the surfaces, and so these provide another exciting prospect on Titan. I said before, we think that life requires a solvent, presumably water. Well, I mean, that's life as we know it. What if there's life, but not as we know it, Jim, here? There's certainly a possibility that we can't rule out that prebiotic or biotic processes might be able to operate in liquid hydrocarbon. We don't know if that's true or not. There certainly seem to be a lot of barriers to that, but we thought there were a lot of barriers to life at the bottom of Earth's ocean and in highly alkaline and acidic environments, particularly, where we've shown that life has thrived on Earth. So we'd like to keep open the possibility that perhaps there might be biotic or prebiotic processes in Titan's lakes and seas. And so that's why we'd like to investigate the composition of the organic material as well that may have been processed through these lakes and may have, you know, been able to represent the history of the chemistry that occurred there. So stay with me. Where we're looking for that material is not in the lakes themselves, but rather in the sand dunes. Okay, so that seems like as far as possible from the lakes. At the same time, if you think about it, if you're to look for life on Earth, would you really land in the middle of the Pacific Ocean? I don't know. I think that would be a very relatively low probability environment. And if you're actually looking for organic material, I'd rather look sort of at the edges of oceans, maybe in a lagoon or a beach, and look at the oozy stuff that washes up. It sort of concentrates that organic material in a way that's much easier to measure than it might be at the parts per million level you could get in the lakes themselves. The Titan sand dunes are the epitome of that. So this is a picture of the sand dunes from a radar instrument. So that's why it looks kind of splotchy and black and white. But these long linear bits here are Titan's sand dunes. Their spectrum in the near infrared and their emissivity properties in the radio are indicative that they are not made of water ice, which we might have expected, right? The surface is water ice, but instead, the composition of these seems to be consistent with organic material broadly. But surprisingly, the scale and size of these dunes is really similar to the dunes we see on Earth in the Sahara Desert, in the Arabian Desert, and in the Namib Desert of Southwest Africa. They're about 100 meters high, maybe. They're separated by 2 to 4 kilometers between each sand dune, and they continue just for hundreds of kilometers without intersecting each other. So I've been fortunate enough to visit one of these analog places here on Earth, because we're not going to be getting to Titan anytime soon, to be able to do that measurement. And so this is what we think that dune area will look like on Titan, based on the ones in Namibia in Southwest Africa. Okay, so here, this is about a 100-meter high dune. You can see the other dunes parallel to us on both sides. And this dune just keeps going. We drove tens of kilometers down, and that looks very similar to that whole distance. Surprisingly to me, someone from an astronomy and physics background, inside these longitudinal dune fields, only 40% of them are covered in sand. What you get are sand dunes, and then flat interdune regions between the sand dunes, and then another sand dune. And you can see these interdunes over here. So what's exciting about the interdunes is that they're flat, they're safe to land in, and they're composed of background rock. They're not made of this sand material. So this was exciting because it's a place where you could potentially, if you had mobility, you could land in either the dunes or the interdunes and be able to drive or fly to the other one really easily to be able to measure. On Titan, remember, the dunes are organic, so you could measure the organic material in the dunes and the icy material in the interdunes. So that was what we designed Dragonfly to do. I thought about using a wheeled vehicle, but for those of you that have followed the Mars rovers, wheeled vehicles and sand dunes don't seem to get along. So did not seem like a great idea. And we thought we probably needed some flight mobility to be able to make sure we negotiated a safe landing site anyway. So what we came up with was Dragonfly, which will use 8 rotors. So it's an octocopter technically, to be able to achieve mobility on Titan the same way that we've done on Mars using wheeled vehicles, but here we're going to do it by flying around. What I told you, we call ourselves, yes, we're an octocopter, okay, but we really think of ourselves as a relocatable lander, meaning that we spend 99.99% of our time on the ground, and our science is on the ground. We only fly to be able to get between suitable surface locations to be able to execute our science. So yes, we're a quadcopter, but it's not like we're gonna be like zooming around through canyons and stuff. Most of the time we're just on the ground, and then once every Earth month, every 2 Titan days, we're gonna take off, we're gonna fly for maybe half an hour, 45 minutes. We'll get to our new location and we'll be able to do a whole new landed mission in that new location. We can also, if we land and we see something really interesting, like right over there, we're able to lift off and translate a couple meters over to do science too. But for the most part, our science is on the ground. We have 4 different science instruments. Our primary instrument is the gas chromatograph mass spectrometer, whose responsibility will be to identify the composition of surface materials. It's this organic stuff that's falling out of the atmosphere that's accumulating on the surface, and that we think is mixing either in liquid water or liquid hydrocarbons, that we find most scientifically interesting and is one of the least explored aspects of Titan. So this is really our Cadillac instrument, is a very sophisticated mass spectrometer based on the one on Mars right now on Curiosity, that will be trying to do that measurement for us. Complementing the mass spectrometer is the gamma ray and neutron spectrometer, whose job it is to, I mean, the mass spectrometer is measuring molecular mass, it's measuring molecular composition. The gamma ray neutron spectrometer is measuring elemental composition. So some elements like sodium, for instance, don't volatilize very well, and the mass spectrometer isn't going to be able to identify those. But the gamma ray neutron spectrometer will. Will be able to measure the broad elemental composition of what atoms are around within a couple meters of the lander. And we want to use this to complement the mass spectrometer to look for heavier elements and to just determine, broadly, are we on, or have we landed on organics? Have we landed on ice? And so this is a complementary measurement, really. We do have 8 cameras, which will give us very exciting views of the surface. I'm looking forward to. We have 2 forward-looking cameras. We have 2 panorama cameras that are located up on our radio dish here. We have a flat phased array dish so that it doesn't create more drag while we're flying. And this will fold back onto the back of the vehicle while we're in flight. But these 2 cameras, the dish will be able to rotate those around and generate 360-degree panoramas of our landing sites when we get there. We also have 2 more cameras, 2 that are looking down at our skids down here to where we're going to do our sampling broadly. And then we have 2 microscopic cameras that are going to zoom way in, okay, and look at individual sand grains, basically, look at their shapes and sizes, and look at the characteristics of the drill hole that we've created. Our last instrument is dedicated to atmospheric and geophysical monitoring. So we're going to measure the temperature and the pressure, methane humidity, wind speed and direction. And we do have a seismometer on board, which is particularly exciting, I think, in that we just have no idea, basically, what we're going to be able to see in terms of earthquakes, Titan quakes, on an icy world like this. Titan, like Europa and other icy worlds, is being needed by tides from Saturn, and so we expect there to be seismic activity and seismic signals, but no one's measured anything like this anywhere but the moon so far. Okay, we just started measuring them on Mars. So it'll be really exciting to get a sense for the seismic activity level and potentially even the interior structure of Titan from our seismometer. So they always say when you're designing one of these spacecraft on a CAD model, right, you kind of look at it on your computer and you think you know how big it is. It's got a scale bar, you know how big it is. And they always say it's going to be bigger than you think. So at our site visit, I was able to be with our Iron Bird, is what we call it, just a mock-up of the full size. Obviously, this is never going to fly, but just a full-scale mock-up of the vehicle. I knew it was going to be bigger than I thought, and it's even bigger than that, okay? When I say it's a quadcopter, you think of something that, your kids got from grandma that, flies around the living room. This is half a ton. It's 500 kilograms, roughly, in mass. It's about 4 meters long, 3.5 meters long. This is my former graduate student and now co-investigator on the mission, Shannon McKenzie, as a scale bar. You could basically lay down in the middle of this thing and go to Titan if you want. I mean, there's not a lot of snacks, so I don't recommend it, but it's big. It is a really big vehicle. And the other thing this image demonstrates is our sampling system. How many of you guys saw the really cool sampling that they did at the asteroid Bennu from OSIRIS-REx the other week? Anybody see that? Okay, there's only 3 of you with your cameras on, so I can't see everyone nodding. Okay, right, they had this crazy system, right, where they had the arm, okay, and it was gonna push into the asteroid, and then it releases this can of air, and then the air agitates all this stuff, and then it had to capture this rock, and then it had to close off the thing, and then it had to put the, because if you're trying to sample on a zero gravity object, it's really hard. Similarly, the Mars Phoenix mission that John Moore's worked with, when they tried to sample with a shovel, they shoveled material up, and then they tried to put it in their sample container, and it got stuck because Mars only has 40% of Earth's gravity, and the soil had a much higher cohesion than they had assumed. So sampling dirt in a planetary context is challenging, and Titan is the one place where it's easy. We sample dirt on Titan the same way you sample dirt in your carpet, with a vacuum. So we have vacuum blowers here that provide suction, and then we have vacuum lines that run through our carousel and sampling system up here and the mass spectrometer down to each of 2 drills and sampling sites, one on each skid. So what we're going to do is we're going to drill into the surface to create sedimentary material, so small grained material. Then we activate the vacuum cleaner. We suck it up to be able to bring it through the system, sample, branch off a little bit of that sample to be able to run through the mass spectrometer, and we exhaust all the extra stuff back onto the ground here. I'm really excited about this sampling system, okay? I think Titan is the easiest place to use the vacuum sampling system anywhere, obviously, okay? Like on Mars, there's not enough air to have it be worthwhile, and on Venus, a vacuum is basically a blowtorch pointed inward. So that's not very helpful either. So I think this is going to be really enabling, and has been enabling, for us to be able to get huge amounts of material, right? If you're looking at sampling Enceladus plumes, for instance, you're looking at getting just very, very tiny amounts of material to be able to sample and then explore for composition. Here, we're going to have like cubic centimeters of stuff that we just have to get rid of because we don't need it all. So we have a very large mass of sample that's afforded to us by the easy sampling at Titan's thick atmosphere. Here's the principal investigator of the mission, Zibby Turtle, showing the size of our rotors. Like, these things are fat. Like, this is a little smaller than a Cessna propeller, and we have 8 of them. Okay, this is a really big, intimidating system. And you know, when I drew this, Ralph Lorenz and I drew this on the back of a napkin 4 years ago, like seeing this whole thing like actually come together, and like, it's intimidating. Like this big thing. There's like hundreds of people working on this now. It better work. It better been right. Okay, so how are we going to get to Titan? This slide is old, because when we were selected in the summer, last summer, well, not summer of 2020, but summer of 2019, NASA selected us to launch at our backup launch date in 2026. And just last month, due to coronavirus budget situation, we got pushed back to launch in 2027. So we're still trying to figure out exactly when we're going to launch. But when we do, regardless of when we launch, we will have at least one gravity assist through the inner solar system. So we'll fly by, our nominal here was to fly by Venus, Earth, and then Earth again. We expect something like that on our way out this time as well. And our cruise will take between like 6 and 10 years to get out to Saturn. Which, gosh, you know, it's just, when you're exploring the outer solar system like this, you just have to think ahead. I'm very jealous of John, and who gets to fly to Mars in 6 months, and then woo, you're there. In the outer solar system, you really have to, it's almost generational in nature, right? The previous generation of planetary scientists built Cassini that Catherine and I worked on, and now we're working on the next mission that I think my marbles will still be not rolling around too much by the time we get there. But we're fortunate we went when we did, because this whole process takes, you know, from when we first conceived of the mission and proposed it till when we land will be 20 years. So it's a long time frame that you got to think ahead for. All right, so the last thing I wanted to do was to show what it's going to be like when we arrive. So this is a movie of our arrival. So here we are slamming into the Titan atmosphere at 7 kilometers per second. Many of you have seen landings on Mars, which they call 7 minutes of terror. For Titan, it's more like 2 hours of concern. So it's not so bad. Not that we're not going to be freaking out, but it's not nearly as harrowing as a Mars landing, because that thick atmosphere is just provides a nice soft pillow for us to land on. So as we come down, man, I don't know what's wrong with my laptop these days. Okay. There we go. All right. We come down, we eventually ditch the parachute and start flying off on our own. Wow, that is just terrible. All right, so I apologize for that. Let me see if I can find that movie. I can show it to you without the PowerPoint getting in the way. All right, here's the movie straight up, where we're flying in. We do have to have a couple of parachutes just to stabilize our descent, mostly, not so much to slow us down. And then to be able to ditch this heat shield, which we need to be able to survive the fiery reentry, but then we need to get rid of so we can expose the lander. So when we do that, here we are hanging out in the aeroshell, and a lot of the shape of Dragonfly actually is designed around exactly this. How do we fit it inside the nose cone of the rocket and inside the aeroshell? So that's why we sort of have the configuration of having most of the material in this candy bar in the center and having the rotors around the edge like this. Once we're down to about 4,000 feet elevation, we will deploy the lander. And because we're not on Mars and we don't have a finite amount of fuel, we can fly for half an hour. We don't have, you know, a 60-second fuel that we have to put down exactly where we land. So we're going to actually fly around the surface and explore the surface with our LiDAR to make sure we find a place that's both flat and free of obstacles, and we'll be able to put down there then. We'll be able to stick out our antenna, turn it to Earth, and start uplooking data. So that will happen whenever we get there on this new plan, either 2034 or 2036, probably, is what we're looking at. Okay, so we think Titan is an exciting one of these new ocean worlds, and one that's particularly accessible and interesting because it has this exciting organic chemistry combined with the liquid water and methane lakes. We're really using the rotors to be able to achieve mobility on Titan the same way that the rovers have done on Mars. And really our science goals are looking for prebiotic chemistry, exploring potentially habitable environments, and yes, we're going there. We are going to have as an explicit goal of the mission to search for potential chemical biosignatures that might indicate that life either exists or has existed on Titan's surface. Okay, I went longer than I expected, so I look forward to your questions. How do you guys want to do the?
Yeah, so at this point, if anybody has any questions, just use the participant tool at the bottom, and I'll call people out. So we'll go with Professor Isaac Smith.
Hi, thanks for the great talk. It's very exciting to see this mission fly. I think it's one of NASA's most bold missions in a long time. So I'm really glad you proposed it and it got funded. I want to say a couple of things. One is that to me, it doesn't look like a candy bar. It looks like a sled. I don't know if it looks like that to you, like snow sled, especially in the winter. And then are there risks? So do we know the wind speeds well enough that we could choose to fly anytime, or do we have to monitor the wind speeds? And then are there other weather hazards like potential rain or something like that that would affect the mission?
Yeah, good questions. Huygens was able to measure the winds near the surface, and they're in the kind of tens of centimeters per second typically. We do think that there are occasionally storms that mobilize the surface sediments and the dunes in particular that might get up to 1 or 2 meters per second. We can fly it up to 12 meters per second, so this is a concern. but we can overcome that in order to make sure that we can land. Rain is possible here, but we are landing in the sand dunes. We're landing in the desert. We're landing in the dry season, and as you saw, even in general, a very small fraction of Titan is covered in cloud. So on average, we think it lands on, it rains in any one place on Titan, maybe once every 1,000 years. On average, there's some places where it gets a lot more rain and some places where it gets less. But even with all that, we don't think the rain's a big deal. Like the big problem if you leave your iPad out in the rain on Earth is that the water will short out material, deposit minerals, will start to eat at and rust the material on the inside of your phone. But if you bring your phone to the Genius Bar and you need to get the water out of it, they actually dump it in a non-polar solvent like acetone or something to drive the water out. The methane and the stuff that's coming down here is all non-polar. So the risk of it getting in and damaging material, it's not a problem. The biggest problem actually with rain is thermal. It will cool us off. We use our nuclear battery here, the nuclear radioisotope generator in the back to provide waste heat and electricity, and the waste heat keeps us warm on the inside. So it's really the evaporative cooling of rain that might be the biggest danger, but we've calculated we're extremely well insulated. So it'd only be a couple Kelvin difference, and it's something that we should be able to handle. Despite all that, we do have a special set of engineering wind sensors and temperature sensors and pressure sensors. And if we're scheduled to do a takeoff and do a flight and suddenly the pressure starts to drop and starts to get windy and the temperature drops, we'll abort the flight and we'll radio back to Earth for help to see what we should do. So we think we can survive all the weather conditions, but even given that, if there's anything shady at all, we just abort and fly at a different time. And that's a real advantage we have, I think, is that we're safe sitting on the surface. And if we just do nothing, we're probably fine.
I feel safe. All right, thanks.
Professor Nicholas Cohen.
Yeah, so I have more kind of technical nuts and bolts questions about Dragonfly. So first of all, on the landing, you're like inside of this like upside down cup. How like tight is the decision point where you have to come out from under the cup, or is there a plan B where the cup actually lands and now you're like a beetle caught under a cup? And do you have some way to poke the cup off of you?
I mean, it's been suggested maybe we leave that on there for the initial landing, but the last thing you want is to have, the parachute land right on top of you or something crazy like that. And so that's why it's a pretty safe operation here. Basically, the lander is heavier, is most of the mass, and the back shell has this huge parachute to increase its ballistic coefficient. So all you have to do is cut the bridle and let the thing go, and we will naturally just fall out from underneath. So there's really not a real chance that we could get caught in there unless somehow that cutting mechanism fails, and it does have a backup. So we are attached at that point, but this is the more scary thing, at least to the review panel, was how do you start flying if you're just falling uncontrolled out of a parachute? And we've done a bunch of simulations of that, including a physical simulation. We had a drone carry another drone and had it drop it and have it activate from different just falling through the air like that. And it seems to work every time. In fact, we think we can even recover from an upset if the thing is swinging around and doing something crazy. Our ability to control the vehicle and to be able to know what direction we're pointed and everything is good enough. We think we can recover from any deployment attitude and velocity.
So that's a perfect segue to my next question, which is like artificial intelligence, like how. Because presumably you're not going to like be flying this thing with a joystick given the light travel time. So like the AI for drones is that good now? Like I only ever see like kids in the neighborhood flying these things. I didn't know that the AI was that good.
Well, I guess I wouldn't call it AI because it doesn't involve a neural net or anything. Maybe that's just a mischaracterization on my part. Yeah, we definitely are able to use algorithms to be able to maintain attitude control and to navigate. And as you point out, we're 80 light minutes away, so there's no one with a joystick driving this thing around. It's got to be able to fly entirely autonomously and figure out what's going on. Most of the danger is actually in that very first landing, because our pixels on Titan are about half a kilometer on a side, so we don't know what the hazards are at a local level. So we fly along at progressively lower altitudes to look at surface tilt. We can survive tilts up to 10 degrees. That's the requirement. So we look for the flat places, and then we kind of circle back down and we fly over those flat places and we look for rocks. We want to maximize our distance from rocks that are bigger than about 30 centimeters or so. And so we're able to do that with the LiDAR as we come down. And then once we find a place that maximizes those things, the flattest, most boring parking lot we can find in the area we're at, we're going to put down at that place. After we've landed once, though, we have this strategy where we could fly as far as we want, as far as we can, and then land. But that's not what we're going to do. Instead, we're going to fly out sort of 2/3 of our range, take pictures of the surface, and then fly back 1/3 of our range and land here. That way, every site after the first site that we land at is going to be pre-scouted. We'll have uplinked all those images to Earth, and scientists will want to find the really interesting places to go, and the engineers will find all the really boring flat places to go. And we'll come to some agreement in the middle as to where to go. But that's really just that first landing that's going to require all of our autonomy. Since we have that, though, if there's an emergency, we will engage that autonomy at any time, right? If there's like, oh my gosh, we have to land, then we'll do the same thing where the computer will find a safe site again.
If there are no further questions, then, oh, sorry, there's another question by Chase. Chase, go ahead. Sorry, Chase, I had to mute you. There was a lot of static.
Hey, here you man. I didn't know you were there. What are you doing in Canada?
No, it looks like, if possible, Chase, could you write your question in the chat? Oh, yeah, okay. Chase just said, give me a second.
Yeah, Chase was a former student here at Idaho, so I didn't know he was in Canada.
We do advertise these to quite a broad variety of people, and we've got about 50 people outside of the country.
All right, so his question is the seismometers, and are they on the skids, or how coupled are they to the surface? So we actually cheat. We have those geophones, which are on the skids, and they're coupled, okay. They're not great. They're not great. Okay, I thought, okay, that makes more sense. All right, so he's attaching from Atlanta, but they're just whatever the vehicle is on the surface, and the surface very well maybe, we might be on a rock or something, and so the coupling there is, not great, but the idea is these are really pretty fool and fail proof in that they're going to get something. They're fixed on the skids. They're not very complicated. We also have a much more delicate and sensitive, but also potentially risky seismometer that's being built by JAXA, the Japanese Space Agency, that's located inside the vehicle up here. And it's actually lowered down on a bridle, and it will be lowered onto the surface while we're at what we think are appropriate landing spots to do much more better coupling, less coupling to the vehicle, which is going to be providing a bunch of spurious seismological information, and then we'll reel that back in before we take off, so it doesn't provide a bunch of drag. But that's our strategy. We sort of have both, right? We have the geophones on the skids that we know are going to work, but are less sensitive, and then we have the sensitive one that's sort of a little bit more risky and has to deploy in order to be able to get it down to the surface. Bye, Catherine.
So if there are no further questions, I'll just ask if everybody could unmute themselves and maybe just give Jason a round of applause. Awesome.
Thanks, guys.
Yeah.
Wish I could have seen you in person next time, maybe.
Yeah. But that concludes our seminar. Thank you again, Jason, for the wonderful talk. And I'll see everybody on December 2nd for the next one. All right. Take care.